Today we're going to talk about chemical kinetics. Chemical kinetics talks about how fast reactions occur. Earlier we had talked about thermodynamics, which talks about the energy involved and whether things would occur or not, and whereas kinetics talks about pace and how fast reactions will occur. So there's one major theory that we'll want to keep coming back to that will form the basis of everything we do. It's called collision theory. In order for a reaction to occur, molecules have to do three things. They have to collide, they have to collide with sufficient energy, and they have to collide with sufficient energy and the right approach. So we're going to use that the whole time that we're discussing kinetics. Here we have a hydrogen, we have a bromine, and together they're going to end up with a hydrogen bromide. What we haven't necessarily talked about a whole lot before is what happens in the middle. And so when they react, they collide, the hydrogen will collide with the bromine and creates this funny little thing here called a transition state. And so the bonds are being partially formed, other bonds are being partially broken, and on its way to being product. So this is called the transition state or the activated complex. Now, before we looked at energy diagrams, we started with reactants here and products here, and we said that this would be an endothermic reaction in this case, and that would be the end of it. However, now we have this additional little bump in this situation. So when the hydrogen collides with the bromine, you end up with this kind of spot right here. Molecules must collide with sufficient energy. This is the amount of energy that they have to do. How hard do molecules have to collide? Well, if this hydrogen just touches the bromine, they're going to kind of increase in energy a little bit, but that's all. And then if they hit a little harder, they'll kind of hit here, and then that's about all. They have to collide hard enough so it can start to break the hydrogen-hydrogen bond and the bromine-bromine bond. And so that energy is called the activation energy. We had looked at thermodynamics before, and we had looked at the difference between the reactants and the products as being the delta H of reaction. And so that still goes there. And so that would be this distance right here, all the way up to there. So that's still the delta H, just like it was before. But now we have the activation energy, which would go from there all the way to here. There we go. So, factors that affect the kinetics. And so temperature is an issue. When I have these molecules come along and colliding, they're going to collide and hit and bounce. Now if they just touch, there won't be enough energy to start breaking the hydrogen bond and start breaking the bromine bond. And so as you increase the temperature, the kinetic molecular theory says that molecules will start moving faster, and so they will collide a little harder, and then collide a little harder, and finally if they get enough temperature, they will collide hard enough to start breaking those bonds. So if you increase the temperature, one of the factors is that they collide with more energy, more chances of having enough energy to get to that mountain on the top, the transition state, and so a faster rate of reaction. Temperature has another impact on kinetics as well. In addition to the molecules colliding more forcefully, they will collide more often. So if they're moving around and they collide here, but they don't collide quite with the right approach, then they could bounce off here and bounce off here, and maybe they would collide with that one, and maybe this one would hit and bounce and hit and bounce and hit and bounce and hit and bounce and then hit and bounce and react with that one. And so the more they are moving around, the more collisions are happening. So the collision theory says they have to collide. Because molecules are moving faster when it's warmer, the number of collisions increases. That increases the chances of having a successful impact. Temperature also affects the kinetics because in addition to colliding more often, they collide more forcefully, and now the chances of having a collision that gets to the transition state grows. So it turns out that a general rule of thumb that if I increase by 10 degrees, I double the rate of reaction. Concentration has an impact on the rate of reaction as well. If you only have two things moving around, this guy is going to go over here, and that one could be moving over there, and then that could be bouncing off there, and that could be bouncing there, and that could be bouncing. And so they could take a fairly long time before they actually ever collide to do something. And so if we increase the concentration, what we have done now is we've increased the number of collisions. So this may collide but not have the right amount of energy. And then it may bounce over here and have sufficient energy but not the right approach. And so then maybe finally over here it collides with that one and it has the right amount of energy and the right approach. The more green molecules you have, the more collisions can happen and with the right conditions, and so your rate of reaction goes up. Fortunately, if we also add some more yellow molecules to this, then the rate of reaction can increase as well, because this green one could get hit by that one but not be quite right, but could get hit by that one and it would be right. And so increasing both chemicals will also increase the rate of reaction. The surface area will affect how fast something reacts too. So let's look at dissolving something. And so here we have a bit of sugar perhaps on the bottom of a beaker, and we've got some water. And so what's going to happen is this water is going to come down and attach itself to the sugar, and it's going to pull that sugar away. Now it turns out that if you're on the outside of this cube, then that's great. There's lots of water around and you can have lots of collisions with water. However, if you're on the inside, you can't dissolve. You have to wait until something else happens. Okay, and so if we go to the next slide, if we increase the surface area, so we break it up, now all of a sudden you have much more molecules of sugar exposed to the water. So this edge right here that used to be hidden is now available for water to come and hit, and for water to come and hit. And so now you have lots more areas of attack. And so you've increased the possibilities for collisions. Compare that to this situation back where we have the full crystal, then your modes of attack are limited to the outside. And so you're going to have to wait for a while for the outer sugar molecules to be dissolved before the inner ones can. When you have lots of surface area, you have lots of modes of attack. And so if you take a big chunk of coal and throw it in a steam engine, you get a nice good fire and you can get from one place to the other. However, if you have coal dust, like in a coal mine, and a simple spark, then the rate of reaction is so fast because of the large surface area that you end up with an explosion. Now, catalyst is an interesting thing, and it impacts the kinetics. What it does is it will change your energy profile from something with a large activation energy, and then when you add a catalyst, it gives you an alternate path. And so now reactions, collisions that might get up this far onto the reaction profile, but not enough to make it over, would in the past been fails. But now, because we have this catalyst, a collision that wasn't quite strong enough now does have enough energy to make it over top of this new pathway. And so that's the impact it has on the reaction profile. It lowers the activation energy. So the activation energy now, instead of going from here all the way to the top, now it's only from there to there. Lower activation energy, more chances of collisions having sufficient energy, faster rate. The next step to that, though, is how does a catalyst do that? How does it lower the activation energy? Suppose we have a carbon-carbon bond, a double bond, and we're going to add hydrogen to this. And so then over here on our products, we end up with C, H, H. And so here's our reactants, here's our products. And what happens to that transition state at high energy? Well, normally this C double bond would have to break. And that might be difficult to do. And so you can make this happen, but it requires high temperatures. Do you really want to have high temperatures and hydrogen around, surrounded by hydrocarbons, which are also very flammable? It sounds like could be a difficult situation. So you can do this at lower temperature, but then you'll wait forever, or you can do it at a higher temperature and risk some damage to a bad situation. Suppose we were to go to add some platinum. Now, what will happen is platinum is attracted to this double bond here. So those two electrons that were originally shared between those two carbons, they now get shared with the platinum. And so before, this hydrogen molecule would have to collide and try and break a double bond. And now what it's going to try and do is it's going to break a bond in half. And so this strong bond up here has now been weakened. And so now collisions that normally would just bounce off, they weren't strong enough to break the double bond, are now strong enough to happen, and so the activation energy is lower. And so you end up with that situation where you have a large activation there, and now you have with the red a different pathway because the platinum has weakened that bond. Mechanical stirring. So mechanical stirring is a factor in kinetics. Here's our dissolving sugar situation again. And so water might come down. And so water might come down and attach itself to a sugar. And so you end up with a little bit of sugar with a bunch of water around it. And this happens time and time again. So here we have our water molecules with their sugar attached to it, solvation spheres around our sugar. And it gets to be quite a crowded spot. Now these molecules are moving around a little bit, but they're not necessarily moving very quickly. And so there's more sugar to be dissolved, and there's a fresh water molecule here that would love to do some dissolving. However, in order to do that, it's got to weave its way through these molecules, and it can do that, but it's got to wait. And so at natural motion of molecules, eventually what will happen is one of these will kind of move along on their way, and now fresh water can come in and do some dissolving. But now that spot is taken, and this water molecule's got to wait for a little while too. If you do mechanical stirring and you put a propeller in there or just a wooden spoon and you give it a swirl, then what that does is it flushes all of these things out of the way and encourages movement to happen and encourages fresh, new water to have access to the sugar all the time. And so fresh water doesn't have to wait for there to be an empty space before it can attack and do some more dissolving.